Negative x squared plus 7x. No, 6x. 6x? 6x, right? Minus 7. Do you all agree? Yeah? Anyone have a question on what I've done? I'm seeing some raised eyebrows. Did I do everything right? Negative x squared, 6x. So we're good?
Yep.
Okay. Look at what we have. At the end of the day, if we're on L3, we reduce it down to our surface really being just a function of a single variable on a closed interval. And we have the Cal1 technique now, right? Now this is not a line, so we can't just check the endpoints. We actually have to find the critical points. So now what I do is I take the derivative. I'm going to erase this. I don't think I need it. So I'm going to take the derivative of this. The derivative of that function restricted to that L3 should just be, well, this is just our classic derivative, right? Negative 2x plus 6. What do we do with that derivative? Set it equal to 0. So when I take that derivative and set it equal to 0, I get negative 2x plus 6 equals 0. And solve that, and I just get x is 3. Okay. And if x is 3, I know something interesting is happening here, right? So in terms of a point for our surface, if x is 3, then the y is what? 2, right? If I replace that x with 3, negative 3 plus 5 is 2. So this is the critical point. Something interesting is happening here. And where else do I need to check? Because I'm not done. I have to check the two endpoints. But the good news is, aren't those two endpoints, didn't we already check those on L1 and L2? We did. I'm going to write them down still, but I'm just, I want to point that out. So now I'm going to take the original function, evaluate it at 3, 2. I'm going to evaluate it at, when x is 1, right? And when x is 5. When x is 1, what's y? 1, 4. And then the other one is when x is 5. When x is 5, you get 5, 0. Okay, I already did these. What were them? What were they again? These two bottom ones? At 1, 4, we were at 2, right? Negative 2 here, and this one was 2, yes?
No, it's negative 2.
Oh, it's negative 2 as well. Okay, negative 2 as well. And then 3, 2. We haven't done that one, have we? I think this is where we're going to have an absolute maximum in, though. No, maybe not. It's 3, 2, 2, isn't it? When you plug in 3, 2, you get 2. Okay. There we go. So let's get a final conclusion. Actually, in the notes, I worked this out, but it's all typed up, and if you hadn't seen it worked out, this might be hard to read. Let me get to the conclusion, which is that final box right there. Our conclusion is that at 5, 0, negative 2, and 1, 4, negative 2, these represent our absolute minimum value of that function on that region. There were two different points in which we got to our lowest value of negative 2. And then at 3, 2, 2, and 1, 0, 2, we had our absolute maximum, and that maximum value was 2. So visually, you can see these points now that I've found them. You can see them here. I'm going to bring that surface in. There's the region. Is this the problem? No, that's the next one. I went on to the, sorry. Here we go. So here it was, right? We moved along line 1, line 2, line 3. I have them labeled different here. I did line 2 as the diagonal. But we got these points. What I think is the cool one is, see the one that's along the triangle, this side, the hypotenuse? If I look at that from the side, do you see that? Do you see the parabola? Right? You'll see the parabola. And what we did is we found like the maximum of that parabola. It's kind of cool, right? You're taking this region. Your first step one, you're just going to look on the inside and see, do I have any like places where I might have some peaks and valleys? And then you're just going to work your way around the regions. Tedious, right? This is tedious. It's tedious, but it's, I'd say it's not, well, I can say what I want to say. But here, look at this one. How are we doing on time? You have a moment to look at it. I see some tired eyes out there. Yeah, spring break's almost here. Yeah, we haven't done much, have we? Wait till we get to Lagrange. We might get 2 problems in one day. They can be rough. All right, everyone have an opportunity to look at this? You're being asked to find the absolute max and min. So then you're gonna have to go through this like 2-step procedure. First you look on the inside, then you look along the boundary. Now, do you have an idea of what this region is? This is a notation I have not used in here, so let's see if it makes sense. I'm defining this rectangle D to be equal to the set of all ordered pairs, the set of points, that satisfy these conditions. The x-coordinate must be between 0 and 3, and the y-coordinate must be between 0 and 2. So it's just a rectangle, right? In the first quadrant, looks something like this. All my x values have to be between 0 and 3. All my y values have to be between 0 and 2. Everything in there. And what makes it a closed set is the fact that these inequalities have the bars underneath, right? That means you're including the endpoints, so you get that. So do you all see that you're going to have to move around this boundary, and that's probably going to break into what? How are you going to break that up? Yep. Four different lines, right? 4 different lines. Okay, let's do this first step though. First step is like last class. We're going to first find the partial with respect to x. Partial with respect to x is 2x minus 2y. That's it. Partial with respect to y is negative 2x plus 2. Y'all checking me? Yes? That look good to you? Okay, and now I need to set those equal to 0. And hey, check it out. On that second one over there, that only has 1 variable in it, right? So if I set that to 0, I get a solution. I get a unique solution for x. X is 1 over here. And if x is 1 over here, then that forces this over here to turn into this equation, right? If I take that information to this one, I set that equal to 0. And what does that say y has to be? 1 as well. So I have one critical point here. The point is 1, 1. And let me plug that into the function. What happens if you plug in 1, 1? 1? Boring. 1, 1, 1. Okay, so that could potentially be the highest point. Oh, what did I forget? Huh? Well, I've got to do the boundary. Yeah, no, but we got this critical point, right? 1, 1? I didn't check that it was in here. Is it in here? Yeah. Yes, it's in here. Okay, but I forgot to actually do it. Because that would be terrible if you get this, and let's say that happens to be your highest point at the end, but it was never in there, right? So make sure you do that. All right. That's, I think, the easy part of the problem. Now the harder part. Let's go around here. L1, I'll go counterclockwise. L2, L3, L4. All right. Let's talk about what's happening on L1. Who wants to volunteer? Tell me about the points. Go ahead. On L1. Tell me about all the points on L1.
It's bounded between.
What's bounded?
X is bounded between 0 and 3.
Okay, and tell me about what all the points look like on that line. Every point on this line has what do they all have in common?
Y is 0.
The y is 0, and the x is anything, right? As long as that x is between 0 and 3. Now take that, plug that into the original function. So if you go x0 into this original function, it's just x squared, isn't it? And now you're back to Cal 1. You have a function of a single variable defined on a closed interval. So we find the critical numbers of this, right? So we take the derivative of that. And you get 2x. Now we set that equal to 0. And you get 2x equals 0. So the solution to that is 0. Is 0 in here? Yes. Okay, so I keep going. I need to look at my function here, right? These points, I need to plug 0 in for x. And y is 0 already because I'm on line 1. Then what else do I need to plug in? The endpoints. Well, do you see that one of the endpoints is actually this point? Do y'all see that? I don't need to do it twice, so I'm just going to do 3, 0 is the other one. So this endpoint right here coincides to this critical point. All right, that first one, plug in 0, 0, 0, we get 0, and we plug in 3, 0, and we get 9, I believe. Okay, good. Who would like to tell me about L2? I'm going to give everyone, unless nobody else wants it. I'm going to hold off as well. Trying to get some more participation here.
X is 3 for the entirety of L2.
Hold on. L2, you're doing L2, right? So tell me again.
X is 3 for the entirety of L2.
Okay, so on L2, your ordered pair, your x is always 3. So if we're here, x is always 3. And then what's the y?
Any y within
Any y within?
L, 1 and 2.
1, 0 to 2. There we go. Good. Everyone got that? And then we repeat and go through this same process again. Dot, dot, dot. Okay, I'm going to skip this. Who wants L3? The reason I'm skipping this is because in the notes, I actually go in detail about what's happening on L1, what the points look like, what the derivative looks like, everything. It's all here, typed out, written out. Okay, so I don't want to go through it all. But I do want to make sure. Go ahead. So here, your points look like what? X2, your x coordinate's kind of free. Your x has to be between 0 and 3. And then we work that out, right? And then on the last one, L4, who wants that? Yeah?
The point looks like 0y.
0y.
As long as y is between 0 and 2.
Y is between 0 and 2. Okay, and then you work that out. Is that okay if I leave you to do that? Yes or no? It's okay? Because I want to get to the next example because we don't have lines in the next one. We don't have straight line segments. Oh, I do want, because I did type up this code to make this happen, so I may as well show you what I invested energy in. so that we don't lose sight of what's going on. We had some surface, right? We had some generic surface. We restricted it to this rectangle. If we do that restriction, we're only looking at that surface, not the entire surface. We're just looking at the region kind of above that rectangle on the ground. We're trying to find the highest and lowest points, so we walk around with these different lines. When we go L1, we wind up getting a parabola. If we do L2, you're going to wind up getting, it looks like linear. That looks like a straight line if you go L2. And then if you do L3, which is this back side, it's getting rotated. Doesn't that look parabolic? So I think we'll get a quadratic function on L3. And then L4, it looks like a line as well. And so we're finding the max and mins on all those boundaries. And at the end of the day, we'll wind up with a maximum right here in this top corner and a minimum that's going to occur right here along the boundary. That's like geometrically what we're doing. All right. Find the absolute maximum and minimum values of the function f of x equals xy squared on the region D, which is defined to be the set of all ordered pairs, such that your x-coordinate is always greater than or equal to 0, your y-coordinate is always greater than or equal to 0, and you must satisfy the inequality that x squared plus y squared must be less than or equal to 3. So these two pieces of information together tell you that you're in the first quadrant, or on the x-axis up and on the y-axis to the right, right? Your x has to be bigger than 0, your y has to be bigger than or equal to 0. What is this a picture of? Circle, right? Well, yes and no, because it has the inequality. If it was equals, it would be a circle. But because there's an inequality, it's the circle and inside of it, so it's a disk, right? That's a disk, right? If that's an equals, it's just the circle. Inequality says circle and everything in. Now, what's the radius of that circle? Careful. Root 3, right? Not 3, root 3. So I'm going to try and draw this domain. It goes like this. And it goes something like this. Out, square root of 3. Circle up, square root of 3. There we go. Everything in here, right? Everything in here? Do y'all understand this and how this defines this region? Right, first step is to do that part with the partials, right? Where we're not looking at the boundary, we're looking at the inside. So let's do that first. What's the partial with respect to x? These are going to be real straightforward. Y squared, what's partial with respect to y? 2xy, okay. This one, when you set it equal to 0, you only get one answer, right? Y is 0? Ooh, shoo, we haven't run into this before. In order to satisfy the first partial, I moved pretty fast there. Is everyone with me? Okay, in order to satisfy this first partial, I must let y be 0, right? But if y is 0, if y has to be 0, then what can you tell me about that equation over there? It's satisfied, right, all the time, but what's the value of x? What can the value of x be? Anything, right? X is actually free to be whatever we want, which means our critical, does that make sense to you? If I let y be 0, this by default now is always satisfied, no matter what I let x be. But I'm trying to figure out the x and y that make them both 0 at the same time. What we're saying is that y has to be 0 and x can be anything, which means that you're actually talking about what? The segment right here, that sigma. That segment is where I'm going to have critical points along the entire line segment, which means in my next step, step 2, I'm going to cover this. Like it's going to be covered in the next step. So I don't need to actually even concern myself with this anymore. Right? I don't need to. So this right here, after we plug that in, we're going to get that this is 0 for all x that are between 0 and the square root of 3, which turns out to be L1 because I'm about to label it L1. See, L1 covers all these points where the y coordinate is 0 and the x is between 0 and root 3. And then L2, let's make this be L2, yeah? And then the other boundary is this one right here. Now, I could call it L3, but L has meant line, so I'm not going to put L3. I'm going to put C1 for curve 1, all right? If I had nothing but curves, I would maybe do curve 1, curve 2, curve 3. And maybe we could have done that from the beginning, but, you know, hey. C1 represents that curve, yes.
Question, if it was just, your domain was just a circle, would it just be C1, the whole thing?
Well, we would have to probably break it up into 3 different C's because, or 2 at least, because it wouldn't be a function, right? So you would have to do maybe the top half, and then look at that as a function of x, and then the bottom half and look at it as a function of x.
Okay.
Okay, I go, continue. On L1, I think we can knock this out. We've got 10 minutes. Okay, on L1, what do the points look like? X comma 0, and x is between root 0 and, all right, so that's it. I'm not going to work that out, okay? The work is in the notes. I'm trying to erase that. On L2, right, all your points look like 0 for the x coordinate, and the y coordinate is free to be anything between, same thing, 0 and root 3. And I'll let you work that out as well. You plug those in, you see what you get, right? The C1's the more interesting one, okay? Because it's not, again, we have a relationship between the x and y, and it's not, one of them is not fixed. So on C1, well, I'm going to go back to the idea that this is a circle, right? On the boundary, it's a circle. Yeah, just upon this right here. So I know that if I just look at that boundary, it's the equation x squared plus y squared equals 3, right? And I can solve this for y. Square root of, so I move the x squared over and then I take the square root. And I'm supposed to do plus or minus, but I'm only doing the positive because I'm up above the x-axis. So that's what y is, right, as a function of x. And so if I'm on C1, I know that my x has to be x, and my y has to be the square root of 3 minus x squared, and my x value must live between 0 and root 3. Do y'all get that? It's kind of like we did with the line a second ago, right, that hypotenuse of the triangle. We just found an equation. We solved the original, whatever this is, you need to solve it for y and then replace that into the y coordinate. I actually do want to plug this one in. I'm not going to do dot, dot, dot here. What would happen if I took a point that looked like this and I plugged it into the original function? Let's see. Well, x goes in for x, right? So that just turns into x. And then I square the y value. So what happens? Oh, isn't that nice? It squares and goes away. 3 minus x squared. And then distribute through. And you have a third degree polynomial function, right? So then I take the derivative of this, set it equal to 0, get my critical points, test, compare it to what happened on L1 and L2, and I'm done, right? I will dot, dot, dot from there. Because again, this is all here in the notes.
Can it use
The what?
1/4 circumference?
The what?
1/4 circumference
For what?
for C1.
I'm not sure how circumference is coming into.
That length, it's a circle, so you can get 1/4 circumference of that.
But what do we need the length for?
Oh, that's it, you can get that function, so you would insert your L as your R, and insert it inside of your function. Never mind.
Yeah, I'm not, I mean, obviously this is 1/4 of the circumference of a circle, but all we need to do is for a point on this curve, we need to find a relationship between x and y so that we could replace y into our ordered pair. All right, so here's the animation. So we have this really cool looking surface. Okay. And then we're restricting it to just that circle, so our semi-quarter circle. So there's the original surface. Y'all see a little semi-half-quarter circle, whatever you want to call it down there? And then we restrict it to just that, and we get just this piece of it. And then we move along L1 and L2, and I call it L3 here. Or no, I call it L2. Who cares? But do you see along that backside, we get that curve like that? And that's that cubic, that x cubed, that's what it looks like. And then it looks obviously like that's where we're going to find our absolute max, right? Okay, that brings us to the end of this section. Yes?
Would our minimums on that have just been the x and y axes?
Yes, the minimums are going to wind up being anything along L1 and anything along L2, they all spit out a value of 0. So that means your minimum value is 0, but it happens along the entire axis.
Oh, yeah, this is x times y.
I want to show you this problem. You don't have to take notes on this, but please do give me the next 6 minutes if you don't mind. And I really do appreciate everyone being here for this today. I think we made some progress today, even though it was really hard for you to sit through it, it looks like, but it looks on your faces.
Yeah, what's fire weather?
What?
On this computer?
Fire weather? Oh, it's going to get really windy in the next 2 days, so they're sending out alerts that it's going to be like wind gusts up to 50 miles an hour in the next couple of days.
Y'all are out here now where I live on Thursday and Friday. We're under a fire law.
Yeah, because if any, like I was driving down the road the other day, this guy flicked out a cigarette. It's just like, okay, that's a way to start a fire.
I'm over by
Yeah,
So like it's all trees and brush. And
Yeah.
literally, we've been evacuated because of the fire.
You have to be careful with, especially with the wind. Okay, 5 minutes. I want to show you a problem here where, everything's been pretty good up to this point in terms of like our differentiation has been pretty okay, right? Partials have been okay. Here's a problem where what we have is an ellipsoid, okay? An ellipsoid is that egg-looking shape. And what I want to do is I want to inscribe into this ellipsoid a rectangular box. And what I want to do is try and figure out the box that I can put in there that has the maximum volume, right? So this is kind of one of our classic problems from Cal 1, right? To maximize the max-min problems, right? So I want to get it set up, and I want us to appreciate in the next 4 minutes, I want us to appreciate the fact that we don't want to do this problem because it's going to suck. And then when we get to the next section, Lagrange, we're just going to wipe this problem up like it's going to be like nothing. Not nothing, but it's compared to what we have to do here. We're going to get an appreciation for Lagrange because it'll make this problem easier. Okay, so we have an ellipsoid and we want to put a box inside of it. So do y'all see the box in there? And I can change the dimensions of that box, and depending on how I change the dimension, it changes the volume. So I want to see if I can somehow figure out the x, y, and z that give me the biggest volume. So the way I'm going to do this first is I'm going to figure out what is it that I'm trying to find the max of. Trying to find the max volume, right? Volume. So this box that you see, I'm going to run out of time. This box that you see, it lies in all 8 octants, doesn't it? So would you agree that if I just look in the first octant and find what maximizes that first octant, then the rest of it I can get, it's just by symmetry of the ellipsoid that we're in, I can assume that those dimensions would optimize the entire volume, right? So if we optimize what happens in the first octant, we've optimized everything. So I'm just going to restrict our view down to that first octant. There it is. Okay? That's just in the first octant. And I would like to talk about what the volume of that is. Okay? So the volume of that, well, how do I get to that point? I go out an x over a y up a z, right? And that's where I get to that point. So the volume of that box would be length times width times height would be x, y, z, wouldn't it? So the volume of the entire thing, let's go ahead and think about the entire rectangle, would be how many of these boxes? 8 of them. So total volume would be 8 x, y, z. I want to try and figure out how this could be the biggest it could ever be, right? Well, what we've been doing in this section is trying to find the optimum or max and mins of functions of how many variables? 2. How many variables do we have here? 3, right? You need x, y, and z. But there's a catch. This z value has to hit the ellipsoid, doesn't it? If it has to hit the ellipsoid, then it has to satisfy the equation of the ellipsoid, which means that I can solve this equation for z and replace that in here. Let me do it. The volume is 8xy times, now because I have 1 minute, if I solve this for z, here's what I would get, and you're just going to have to trust me on this. Although I'm sure you could probably do it in your head as well. So all I'm doing is taking these two terms to the other side, and then I'm dividing by 4 and taking the square root, and we get this, right? And let me just clean it up a little bit more. Now I'm going to say the volume is now a function of only 2 variables, right? There's only x's and y's in here. Half of 8 is 4, so 4xy, square root of 36 minus 9x squared minus 36y squared. There we go. There's my function of 2 variables. And now I'd like to see if I can find, let's just see if we can find like a local max or local min, right? And maybe we can do that, but what's that going to require? Or what's going to be required for that? Partial with respect to x, partial with respect to y, right? Do you really want to calculate capital D on that? Do you want to take second partials on that? Not particularly, right? I mean, think about it. If you just wanted the partial with respect to x, you got product rule here, right? Nasty. So even though we could continue forward theoretically at this point, it's not something that we really would want to do. In Cal 3 classes in the past, if I've had time, like if right now we had 20 minutes left, I would at least start this and get us to like finally be like, okay, enough, you know, let's move on to Lagrange. So I think you can trust that that wouldn't be fun, right? Yes?
The domain restrictions for it.
So are there domain restrictions?
Yes.
Are there? This is a tricky problem. Think about the domain restrictions. What would it be?